Hi guys. So I'm feeling pretty bad today, but I still want to keep up with the pace of the course and make sure that we have new math to talk about. So I'm going to talk about 5-point B today. And the idea of 5-point B is that we're going to be looking at proving that an operator on a finite dimensional complex vector space always has an eigenvalue. And we're going to do that by looking at polynomials. So remember that this space, L of V, is a vector space, which means operators can be thrown together in linear combinations. But we get more than that because L of V also has the multiplication of anything in the space of operators makes sense because if you're an operator, you map the vector space into itself, so there's no domain issues with that. So t squared, for example, makes sense because t takes v to v. And so if you think about what t squared does, well, t squared is just t composed with v. This t takes v in and spits out a vector in v. And then this t eats that vector in v and spits out another vector in v. And I could do that for any number of applications of the operator t. And essentially what that's going to mean is that we're going to be able to build polynomials out of these things, because if I'm allowed to build powers of operators, then I can put them together using the vector space rules. So let's get that formally codified in a definition. So we're going to say t is an L of v, m is a positive integer, then we define t of m to be equal to t composed with itself m times. And t to the 0, we're going to define to be the identity operator on v. So this is the identity on v. And if t happens to be invertible, if t is invertible, then we can also define t to the minus m, which is going to be t inverse composed with itself m times. And then with that idea, it's easy to show that these operators all commute with each other, which is unusual, right? It's not typically the case that operators commute, but if you have something like t to the m and t to the n, you should check to make sure that the sort of rules that we expect variables to live by actually work here. So you want to check that t of m times t of n is t of m plus n. And you'd also like to show that t of m to the n is equal to t to the m times n. So the idea here is that powers of operators are going to give us the natural structure of working with polynomials. So here's another definition. Okay. So let's let t be an L of v. And let's like p be a polynomial with coefficients in the field. Polynomial of any degree here. I'm not being particular about the polynomials I'm restricting to, any polynomial. And let's suppose that p has the form p of z is equal to a naught plus a1z out to a n a m z to the m. Then we can define p of t for the operator t to be equal to a naught plus a1t plus a2t squared out to am d to the m. The idea here is that we're using the structure of a polynomial to create a new operator from an existing operator t. And so this guy right here is p of t. All right. So it's going to turn out to be the case that all of the operations that we want to do with polynomials, we're also going to want to do with polynomials of operators as well. So remember that if I have P and Q in the polynomials on a field, then you can define PQ to be an F by P of Z, Q of Z, just regular old polynomial multiplication, right? So the space of polynomials is also a vector space that has a multiplication on it, okay? So that means that we have two now vector spaces that have multiplications on them. We have operators, which can be multiplied together, and then we have this space of polynomials that also have a natural multiplication as well. So it's sort of an odd vector space. If you know the term for a vector space where you can do multiplication is an algebra. Okay, so polynomials are an algebra. All right. So it turns out that this multiplication on polynomials translates into a multiplication that works well with operators. So here's a theorem. So if we have two polynomials, P and Q, and we have an operator T, then we have the following. PQ of T is equal to P of T, Q of T, and P of T, Q of T is equal to Q of T, P of T. So this means that this is commutative. Now the proof of this is not hard. You might want to take a look at how this is set up because it's done in sort of index notation with sigmas here. But at least for the second one, it's pretty easy to see what's happening. So A is proved by looking at what the multiplication of P of Z is equal to the sum from J equals 0 to M of AJ, ZJ, and Q of Z is equal to the sum from K equals 0 to N of BK, ZK. You can just build the fact that the formula works here by multiplying these things together, and then what ends up happening is you just switch the coefficients in the formula. So I guess I can write this down. So PQ then is equal to the multiplication of these two sums and if you write down what that means in terms of the distributive property, you get this. Everything gets multiplied by everything else. There's one term for each set of indices, and you're going to get AJ, BK, Z to the J plus K. So this is just the distributive property. And then the fact that we have that form for PQ as a polynomial means that I can actually apply T to it, and I'll get PQ of T is equal to the sum from J equals 0 to M, sum from K equals 0 to N of AJ, BK, T to the J plus K. Okay, and then the fact that we can take this back apart again. I mean, so multiplying the polynomials together got this structure for PQ as a polynomial in Z. That gives us an object that we can put the operator into, and then we can decompose that using the rules for how operators work to just rewrite this as the sum from J equals 0 to M of AJ to the TJ, sum from K equals 0 to N of BK, T to the K, and this is just P of T times Q of T. So the reason that this seems kind of long-winded, the reason you have to do it this way is because if I don't know that P of t and Q of t are equal to PQ of t, I have to start with an object I can plug into by definition. So PQ is the polynomial that we're putting t into. And then I can use the fact that I can manipulate the powers of t to pull it back apart again. What I mean by that is, what we've really done here is right here, we use the rule that t to the j plus k is equal to t to the j, t to the k. Excuse me. Okay. And then in the second proof is easy, because p to the t, q to the t is equal to pq applied to t, which is equal to qp applied to t. And the reason that that's true is because the coefficients commute, and also t to the j plus k, t to the j and t to the k also commute. So to do this step right here, we used commutativity. To the t, and then this is equal to q of t, p of t, again by part A. Okay, so now maybe we have got, I think what I really wanted to talk about today, the upshot of this video is that we can use polynomials to prove, as polynomials of operators, to prove that any operator on a finite dimensional complex Hilbert space has an eigenvalue. And we're going to use the interplay between complex polynomials and polynomials of operators to do that. Okay. So this is a major theorem, and the technique that we're going to use here, which is going to involve applying t over and over again to a vector, that's going to be a technique that shows up in other theorems as we continue through the course. So this is sort of the big dog theorem here. And it says every operator on a finite dimensional non-zero complex vector space has an eigenvalue. Sorry, that's gross, I know. Okay, so this is an important proof because it has a really major idea inside of it. And all of these hypotheses are necessary. If the space isn't complex, we saw an example in the last class of a map, the rotation map, that didn't have any eigenvalues or eigenvectors. And of course, the only way that could happen is if we were in a real vector space and not a complex one. If you're a zero vector space, any operator on the zero vector space must be the operator that sends zero to itself, and those aren't very interesting because zero can't be an eigenvector. And then if you're not finite dimensional, weird things can happen. And this proof doesn't work if you're not finite dimensional because polynomials aren't sufficient in that case. So here's how the proof goes. So let's suppose V is finite dimensional. And let's just give it dimension n. Dimension of V is equal to n, which is bigger than 0. And then we're just going to pick a non-zero vector V. Pick a V not equal to 0, V in V. What we're going to do is we're going to generate a set of vectors that we're guaranteed to be linearly dependent. And we do it like this. We generate the list V, and then apply t to V, and then apply t to that vector. And you keep on going all the way down until you've applied t n times. So the idea is this has n plus 1 vectors. But n plus 1 vectors in an n-dimensional Hilbert space must be linearly dependent. So this list is linearly dependent. And that means that you can find coefficients a naught up to an in C, not the field now, we're actually in C here. So that not all of the AIs are 0, and a naught plus a1, what do I do here? A naught v plus a1 t v plus a2 t squared v out to a n t to the n v is equal to 0. Okay, so now at this point, I notice that I can actually take a v out of all this stuff, right? Every one of these terms has a v in it. And so you actually have a naught plus a1t plus a2t squared out to a n t to the n. But there's a v in each term, so I could think of it as one operator applied to v. Okay, and this is like a p of t. It's a polynomial that t has been plugged into. So the move that we're going to make is we're going to think of finding another way of writing down p of t. And to do that, we're going to turn this into the polynomial p of z, the corresponding polynomial in a complex variable, and then we're going to apply the fundamental theorem of algebra to it. So p of z is equal to a naught plus a1z out to a n z to the n. And remember, we know some of these coefficients aren't 0. We don't know all of them are non-zero, which means we don't actually know if this is here or not. It might be there, it might not be. So when I factor this thing, it might not actually have n terms. So you'll see that right away, because what we're going to do is we're going to apply the fundamental theorem of algebra and rewrite p of z as a constant times z minus lambda 1 up to z minus lambda m, where m could be less than or equal to m. Because, again, I don't actually know if an is 0 or not. So now I've got two different representations of the same polynomial, but if this p of z gave us the p of t up there, well, and this is an equal polynomial, then it's also going to give us the same expression. So what we mean by that is, that means another way of writing down the polynomial in t is c times t minus lambda 1 out to t minus lambda m. And that means I can take this expression and rewrite it as a naught plus a1t out to a n t to the n v is equal to c times t minus lambda 1 out to t minus lambda n v. And all of that is supposed to be equal to 0. So again, what I've done here, this was our original expression that we got by linear independence. Then I've resorted it using the fundamental theorem of algebra and the idea that I can plug operators into polynomials to get another expression that's equal to 0. Well, what does that mean? It means somewhere in this chain, at least one of these t minus lambdas applied to v produces the 0 vector. For some, if we have a non-zero vector and we hit it with all of these operators, one of these things cannot have or must have send a non-zero vector to the 0 vector. For some lambda I, or for some I, t minus lambda I sends a non-zero vector to 0. And that means that t minus lambda I isn't injective. For some lambda I, and that means that t has at least one eigenvalue. Now I've been a little bit sloppy here. I think Axler is better than I've been about making sure that when you do a factorization like this, an expression like t minus lambda 1 or lambda 2 doesn't really mean anything. We have to make sure that when we plug in operators, that if I have a polynomial like P of Z is equal to C plus Z, that P of T, to really be thought of as an operator, I think of taking the identity operator and sticking it in the C, so it makes sense to add it to T. I can't take a scalar and add it to an operator. So that's kind of how you define that move, right? Remember that we talked about, yeah. So this is, I mean, this is the move here, right? When you go from a complex polynomial to a polynomial in operators, the I sneaks in to make sure that the math makes sense. That a constant plus an operator doesn't make any sense. I have not written those in here, but every one of these you should interpret as being T minus lambda J times the identity operator. So even here, there's an identity, and that means that T must have at least one eigenvalue. Okay. And this use of the fundamental theorem of algebra is an idea that comes up quite a bit when we're doing this sort of mathematics. So yeah, so there's quite a bit more to say about this. I'm going to leave this video for now. I might try to record another one later. And yeah, hopefully I'll see you guys on Monday. And I apologize for dragging here. I didn't mean to get this sick. So talk to you soon.